So today I'm going to give the talk about vesicles, the production of these vesicles, which are these spherical shells made of amphiphilic molecules, that is molecules which have both hydrophilic and hydrophobic parts. And particularly as those vesicles, which probably occurred during the origin of life at the beginning of the Archean. So as I mentioned in another talk some time ago, we know that the surface of the oceans are regions of very dense organic material. In fact, they have densities about 10 to the 4, 10 to the 5 times greater than the density of water at greater depths in the ocean. And that is because of the effect of raindrops, for example, which are bubbles. They produce bubbles which carry organic material to the surface. It's also a result of the surface tension because of the air-water interface. And it's also an effect of eddy currents, which could be driven by wind on the ocean surface, for example. So there are a number of factors which produce the effect that at the surface there's a very intense or very dense layer of organic materials. And one of these materials, even today on the ocean surface, are these fatty acids or these lipids, these amphiphilic molecules which have both hydrophobic and hydrophilic parts. So the hydrophilic parts, they stay within the ocean, and the hydrophobic parts are in the air. But if there's a sufficient density, which is known as the critical vesicle density, then they can form these double layers. So for example, here in this diagram here, we have a double layer of these amphiphilic molecules. So the hydrophobic parts are on the outside and the hydrophilic on the inside. The hydrophilic on the outside and the hydrophobic on the inside. And that forms these double layers of which these vesicles are made. So I'll give you the whole description of how these vesicles could have been made at the origin of life on the ocean surface using only UVC light and water which was saturated with carbon dioxide or carbon monoxide. So to get this vesicle formation, we need first of all this double layer of lipids. And this requires a critical vesicle concentration, which I will say more in a future slide, in the following slide. And what we also need is some kind of a force to cause a deformation of this double layer lipid. And with this force strong enough, we can produce these vesicles. And these vesicles, which are spherical, are in fact the most stable. So these, once they become spherical, they will remain spherical. Depending, of course, on the environmental conditions, the temperature and the salt, and also the pH of the water. And all of those environmental conditions we're going to discuss in a future slide. So just from the waves, for example, on the ocean surface, we can produce forces which cause deformations of this double layer, which would be floating near to the ocean surface, and then forming these vesicles, which will remain close to the ocean surface because they have a density less than that of water itself. So today, the cells of the walls, the walls of the cells of all living organisms are made of phospholipids. And these phospholipids have a number of different parts. They have the carbon hydrogen tail, and then they have an ether or an ester linkage, which is this in yellow, and then they have a glycerol and then a phosphate group. So they are rather, and they have in fact 2 of these carbon tails. So they are in fact a little bit complex. It would be difficult to imagine that these were formed at the beginning of life. The difference between the ether and the ester linkage here it has to do with the strength of these vesicles. So, for example, the archaea bacteria, which are in many cases extremophiles, which means that they can live at high temperatures or high or low pH values. They are made of these ether linkage. And most of the other organisms today, which are in more neutral environments, are made up of ester linkages. But as I mentioned, these are rather complex molecules, and it would be difficult to imagine how they came about at the beginning of life through abiotic means. Now, there are some organisms, some archaea bacteria, which are made of another type of lipid, which are known as these fatty acids. So fatty acid had this carbon-hydrogen tail. Okay, it can have some double bonding between the carbons. When we have one double bonding, a single bond, another double bond, that is called a conjugated bond. So this is a conjugated fatty acid. And it has this carboxyl group, which consists of oxygen atom and OH at the end of this carbon chain. And those can come together through an overlap. So this has only a single carbon-hydrogen chain. And it can come together with another one, especially overlapping the part which is conjugated. And we form this overlapping double layer of fatty acids. So they have found them, in fact, in archaea bacteria. There's some bacteria which have almost 80 or 90% fatty acids. And when even the bacteria, the normal bacteria, have a mix, they're not all phospholipids and they're not all of the same length. This is paraenaric acid, which has 18 carbon atoms, okay? And it has 4 conjugated bonds here, double bonds. And the double bond starts at 3 from the end. So this is carbon atom 1, 2, 3. And then we start with this 4 double bonded series, conjugated series. And that's why this is the labeling of the acids. That means 18 carbon atoms long. It has 4 conjugated bonds, and it starts at 3 from the end here, 3 carbon atoms from the end. And this below is linolenic acid. It has the same 18 carbon bonds, but only 3 conjugate bonds. And we'll see that these conjugate bonds determine at what wavelengths these fatty acids absorb ultraviolet light, and how you can very easily change the wavelength of absorption just by removing, for example, a hydrogen atom. If you remove a hydrogen atom, here there are hydrogen atoms, they're just not drawn here. But if you remove a hydrogen atom, then you have an extra bond here to form. So you form another double bond. And as you increase the number of conjugated bonds here, you increase the wavelength of absorption. So we can change this very easily. We can, and in fact, it seems like at the beginning of life, what happened is that we started with this paraenaric acid and then converted this to linoleic acid after the removal of one of these double bonds. We'll see how that can come about. But what I want to mention is that we can form these vesicles, and these vesicles, through this process, if it's inside the water and we have DNA or other organic materials, they can be trapped inside the vesicle. Okay, but as I have always mentioned in this class, the thermodynamic dissipation theory for the origin and evolution of life requires that any incremental complexation in the history of biological evolution has to occur through an increase in the dissipation. So things will start to get complex only if the complexation increases the amount of dissipation that the system can produce. So the complexation, for example, is the formation of these complex prebiotic molecules from simpler precursor molecules. We've seen, for example, the case of the production of adenine, and Claudette is working on the production of guanine. Today, we're going to see the formation of these fatty acids, and later the formation of the vesicles. And their association into cellular or multicellular complexes, that is also a complexation. So if they associate themselves in this kind of a system, a vesicle, then there has to be an increase in dissipation. Otherwise, such a process should not happen, because every process which happens out of equilibrium has to produce entropy. And still another process is the coupling of biotic and abiotic processes. For example, the water cycle with the absorption and dissipation of photons in the leaves of plants today. So for any kind of complexation to occur, and these are the three basic ones, we have to show that there would be an increase, or there could be an increase in the dissipation of photons or some other chemical potential, generalized chemical potential. But in this case, at the origin of life, we're talking about photons in the UVC. So as I mentioned at the beginning, the absorption of the photons, the wavelength, depends on the degree of conjugation. For example, in this case, it looks like we have like 3 conjugated bonds here, but they are not really conjugated because there are 2 single bonds between them. So there's really only 1 conjugation here. And so with 1 conjugation, this is the case of linoleic acid, you absorb at about 217 nanometers. With the conjugation of 2 here, we have a single double bond. We absorb at about 230 nanometers. And with 3 conjugations here, 1, 2, 3, we start absorbing at about 260, 270 nanometers. And this is in fact where the peak in this slide, this picture below, is a graph of the incident sunlight as a function of wavelength in the UVC range. We see where these different acids, fatty acids, are absorbing. Okay, so B, which is this one, which corresponds to these 3 conjugated bonds, absorbs very strongly around the peak. And if you go 1 more, we have 4, for example, in the case of C here, we have 4 conjugate bonds. We absorb now at about 325 nanometers. Okay, so the absorption depends on the amount of conjugation. This is, even though there are a number of double bonds here, it's only a conjugation of 1 because it's separated by 2 single bonds. But all of the others have only 1 single bond separating double bonds. So this is a 3 conjugation, 2 conjugation, and 4 conjugation. That shifts the wavelength of absorption to ever greater wavelengths. Now these hydrocarbons also have this conical intersection. This is the case for butane, which contains 4 carbon atoms. And we can see that if we excite it with a photon, it goes to the excited state. And then it very quickly goes to a different configuration. So there's a change in the nuclear coordinates. And that allows the vibrational state superimposed on the electron excited state to connect with the vibrational states superimposed on the electronic ground state. So we have a degeneracy here in energy, and the system can go very quickly to the ground state by vibrational motion and the energy of vibration being transmitted to the solvent, which in our case would be water. So this is interesting. This is probably the case of the smallest molecule which has a conical intersection. This is butadiene. And you can also see on these graphs are the rates of dissipation. So, for example, we calculate the occupancy of the excited state as a function of time, and it only takes less than a picosecond for the system to decay to the ground state to internal conversion. It's converting the electronic excitation energy into vibrational energy and then distributed into the water. So the system goes very quickly to this conical intersection back to the ground state. So these hydrocarbons, just like we have seen for adenine and guanine and cytosine, thymine, they all have conical intersections. So does these hydrocarbons. Not all molecules, of course, have conical intersections. So therefore, conjugated fatty acids are excellent microscopic dissipative structures in the UVC. So they absorb a photon in the UVC, and with very strongly, in fact, even more strong than the DNA molecules. And they dissipate this into heat, into infrared light, in the order of a picosecond, 10 to the minus 12 seconds. So they're also acting just like the DNA, like small hurricanes. If they are conjugated, of course, if they're not conjugated, they're not going to be absorbing in the UVC range. Okay, so how can we make these fatty acids out of very simple precursors, which, for example, are water, and carbon dioxide or carbon monoxide? We have water saturated with carbon dioxide or carbon monoxide, which probably occurred at the Archean, because in order to have temperatures around 85 degrees centigrade at the ocean surface, we would have needed a lot of greenhouse gases. And the most likely greenhouse gas would have been carbon dioxide. So probably the water, the ocean surface water, was also saturated with carbon dioxide. And we had ultraviolet light in the UVC range over this water. And so what can happen then? We can have this successive reduction of carbon dioxide to carbon monoxide and then to carbon through interaction with the UVC light, and with the help of some ferrous ions, Fe2 plus, or this is one of the molecules in the steps on the way to the production of adenine from 4 molecules of hydrogen cyanide. It's called aminoimidazole carbonitrile. So it's the lowest energy molecule made from 4 molecules of hydrogen cyanide. Maybe you remember that, or you can go back to one of the previous talks and see that this can also be used as a catalyst, just as the ferrous ions, to provide electrons for this reduction process. And then also with the photolysis of water, because of the ultraviolet light lysing the water, we can produce then these molecules, these hydrocarbons, and the simplest is ethylene. Just 2 carbon atoms joined by a double covalent bond with 4 hydrogen atoms. And then we can see, we'll show in the next slide how it can go in, the chain length can increase over time through the action of the ultraviolet light also, and produce these hydrocarbons, these hydrocarbon tails of the fatty acids. So, and another factor which I didn't mention is that the surface of the ocean, that is between the ocean and the air, acts also as a catalyst, and this is known as surface sensitized. So they're just discovering this rather recently, in fact, maybe 5 or 8 years ago, that the surface of the ocean can act as a catalyst also. So that's very good for our theory because that allows us to do a lot more chemical processes which may not have occurred at the bottom, for example, at a hydrothermal vent at the bottom of the ocean. And now I want to give you some evidence that this ferrous ion probably existed at the origin of life, the beginning of the Archean, because we have found these banded iron formations. And this is a picture to the bottom right here of banded iron formations. And this consists of oxidized iron in layers, different layers, which were deposited in the ancient oceans. And in fact, this iron is in fact the iron that is mined today to produce all of the materials made out of iron. So all of the things that you buy from China, for example, the steel works, they're all made from iron, which is coming out of these banded iron formations, which were laid down in the Archean, in the early to late Archean. And so that gives us a very good indication that there was these ferrous ions available in the ocean surface to do this reduction process to produce ethylene. Okay, now this process, let me just say one more thing about this. This process of producing hydrocarbons from carbon dioxide saturated water is a process, in fact, which they are trying to do in the laboratory today. Because, you know, we have this problem with greenhouse gases, which are increasing the temperature of Earth's surface. So the idea is try to convert carbon dioxide in the atmosphere into petroleum, hydrocarbons, which can be used as a fuel. Doing that with the sunlight. Here we're using ultraviolet light, which was available in the Archean. We do have ultraviolet light today, but not that goes down to these wavelengths. We stop at about 300 nanometers today. But it turns out that 300 nanometers may be sufficient with the right catalyst to allow this process to occur. In fact, we do find some of these hydrocarbon chains floating on the ocean surface that could have been formed through the action of light with carbon dioxide in the water. But they're trying to make it now a very efficient process so that we can have a closed carbon cycle, so that we can burn this hydrocarbon chain in our cars, and the exhaust emits carbon dioxide. That's the combustion process. And we have just this cycle, like we have the rain cycle, so we never increase the amount of water in the atmosphere. In this case, in this carbon dioxide cycle, we'll never increase the amount of carbon dioxide if we can replenish it through the petroleum to this technique rather than extracting it from the ground. So that's very interesting work which is being done, trying to copy this process, or not really copy because they haven't realized that this process could have been occurring at the beginning of life. And so they are doing it now through different catalysts and different surfaces, trying to create a carbon dioxide closed cycle so that we end global warming. Okay, so as I mentioned, if we have carbon dioxide in water and we have ultraviolet light, we can produce these radicals. And these radicals can come together and form these chains, larger chains. That is the case in that we have no oxygen, which apparently was the case at the beginning of life. Remember also that at the beginning of life, we had these formation of these banded iron. So these ferrous ions were taking up the oxygen in the atmosphere. There was no oxygenic photosynthesis occurring, so there was very little oxygen in the atmosphere, but whatever was being taken up by these ferrous ions. And that's why the oxygen content at the beginning of life was very low. But every once in a while, you can find an oxygen molecule, even at the beginning of life, in the water. And in the case that you have a radical and an oxygen molecule in the water, then you could form what are known as these perioxyl radicals. And that's what is known as UVC peroxidation. So I will give a little bit more details about what is happening here. This is the production of these carboxyl group at the end of the chain. So as I mentioned, we produce these carbon chain radicals. They can keep growing without oxygen to produce longer chains. But if it encounters an oxygen molecule or a couple of oxygen molecules, it can form this carboxyl group at the end of the chain. And that oxidation effectively stops the chain growth. So at least on this end, the chain will stop growing. So for example, today, the presence of oxygen and the lack of surface UVC light arriving at our surface today means that the production of these hydrocarbon chains would be greatly reduced. Because as soon as we have an oxygen molecule, we stop the extension of the chain, the growing of the chain. But as I mentioned, it does exist. So we do have some production even today, and even with the light, which is not in the UVC range, but at about 300 nanometers, we can produce these hydrocarbon chains. And as I mentioned, the idea is to try to provide a closed carbon cycle and to end global warming with this process. Now, once we have this chain formed of carbon and hydrogen, we have this carboxyl group, then we could have also UVC-induced deprotonation. So for example, absorption of a UVC light releases a hydrogen atom. And as soon as the hydrogen atom is removed from this, we get a double bond. Okay, so the bond, which was from the carbon to the hydrogen, goes to the carbon at its side, and we start forming these double bonds. But they would be formed rather arbitrarily, that is, at random along the chain. So essentially, there would not be conjugation unless by chance it happened to be every second carbon atom which lost its hydrogen. But there's a very interesting phenomenon, and that is known as migration of these double carbon bonds. So for example, if we have the double bonds at arbitrary points along the chain, if you give that system enough time, what will happen is that the double bonds will migrate such that they form this conjugated system. Okay, so the double bond, a single bond, double bond, single bond. So irrespective of where they are on this hydrocarbon chain, they will eventually, under enough time, because it's the lowest energy in the Gibbs free energy state, arrive at this conjugated form, where we have double covalent bonds separated by single covalent bonds. So this is known as bond migration. And this could give DN, 3N, or tetran. So this is 2, 3, or 4 carbon double bonds. And we'll see why 2, 3, or 4 carbon double bonds in this slide. So the conjugation number, as I mentioned at the beginning of this talk, determines the wavelength of the absorption of these hydrocarbon chains. So you remember, if we have only one conjugation number 1, then we get absorption at about 217 nanometers. With 2, we get absorption at about 230, and with 3, about 270 nanometers. So, and if we have 4, which we can also have, 4 conjugate double bonds, then we get absorption about 325 nanometers. And so I have plotted here on this graph of the light arriving at the ocean surface at the origin of life, where these different single, double, triple, and 4 covalent bonds would be absorbing from the graph here. We see that the 3, conjugate 3, is the greatest absorbing because this is where the greatest amount of light is coming in, and maybe also C here, which is 4 conjugate bonds. Okay, so as I mentioned at the beginning, that in order to have the formation of a double-walled lipid layer, we need to have a critical vesicle density. So on this graph, we're plotting the critical density, concentration, as a function of carbon chain length that you need. So we need a certain density